Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll continue Chapter 5, talking about the output voltage for batteries through this two-way analysis of variance. And as you can hear, my cat Zeppo is going to help with the lecture. Right, Zeppo? Yeah. All right, let's see if we can get him away from the microphone that he's so curious about and start this lecture. All right, so we've got a data set here. Let me scroll down to the data set. We're at page 133 of the notes. So the design here is we want to measure what the maximum voltage output is for batteries that are constructed from three material types, and the experiment is conducted at three different temperatures. And we want to understand what the relationship between materials and temperature is. It's a 3x3 factorial design because there's three material types and there are three temperatures. And for each combination of factor levels, there are 4 replicates. All right, so let me scroll up and see if I got that all. Yes. All right, so we're going to read this data from the website, and because we've got numeric variables, we have to manually convert materials and temperature to factor variables for this analysis. Otherwise, the regression model will actually treat these as continuous numbers, 1, 2, and 3, where 3 is 2 units away from 1. But materials don't work that way. Temperatures, we have a choice here about whether we want to consider them as individual levels or we want to treat them numerically, so that each of these are 15 degrees away from, the next one. We'll find in a moment, once we plot the data, that that would be a poor choice and that factor levels are a better choice. All right, so we got data in the wide format, so we're going to reshape it by melting it into long format, keeping the materials and temperatures as identification variables, and then relabeling or labeling which battery we're using, V1 up to V4, and then the value of those variables would be the max voltage. All right, so we now have a data frame, battery.long, with 36 observations. Great. So let's fit the full interaction model with material temp as main effects, as well as the interaction between materials and temperature. And one thing I've pointed out previously is that this multiplication sign actually expands the model out into these three components: the material as a main effect, the temp as a main effect, and material colon temp. That colon indicates the interaction. So when we ask what the effects are, we find that the interaction is significant. In light of that, it's often not very interesting to interpret the main effects, but there are differences by temperature averaged over materials, but not really differences between materials averaged over temperatures. But what the interaction is telling us is that the difference in voltage, let's say for a given material, the differences in temperatures depend on what material you're using. So that dependency is what makes the main effects less interesting to interpret. All right. When we look at the summary, recall that these tests are not that interesting because all these tests are relative to the baseline group in the intercept. Material 1 at the lowest temperature. So we're not going to bother interpreting those for now. All right, so let's create some plots. And first thing we can do is generate some marginal means. So we've got the grand mean. We're going to use the plier package with ddply and take the battery long data set, subset it by different conditions, and then calculate the mean. So first, we're going to average everything. So the grand mean is 105. When you average by material type, we have our 3 material types, and you can see a fairly big difference here, actually 83, 108, and 125 over the 3 material types. When you average over temperatures, we also have big differences, 144, 107, 64. And finally, material and temperature, these give you all 9 averages of the 4 replicates. Okay, and that's what we're going to use to plot the data. All right, so here's a bunch of code. There's 2 chunks here. This chunk is the first plot on the left. This is the plot on the right. So let's just scroll down and take a look at that. All right. So on the left, start off by reading the axes, the material types 1, 2, and 3, with temperatures as colors, and max voltage is the vertical axis. Alternatively, we have temperature as the horizontal axis, and materials being colored, and max voltage being the vertical axis. Which of these tells a more interesting or compelling story for you? For me, it is the one right over here, the one on the right, because it's much easier for me to say material type. All right, material type red. Okay, the first one, what happens as you go from the low to the high temperature? Well, it takes a big decrease, and then it basically stays the same. Material type 3, on the other hand, stays high at low temperature, and then in medium temperature, and then when it gets to high temperature, it drops down. Whereas material 2 is sort of the average. It just has a steady decrease as the temperature increases. Okay, I think it's less interesting, the plot on the right, to do the same interpretations. So just by looking at the plot, what recommendations would you make if it was important to have a high maximum voltage at a range of temperatures? For me, if materials are basically the same in terms of cost, material 3 seems to be the best because it stays quite high, and it decreases, but only at those higher temperatures, but still remains higher than the others. Okay. All right, let's do some statistics. So, the multiple comparisons that we wanted to do using general linear hypothesis test, you'll notice that we get a warning when we try to use this function. Okay, we feed it in the ANOVA object in the general linear hypothesis test, and we get a warning that because there are covariate interactions found, that we don't actually want to, say, calculate the temperature contrasts, because the main effects are not very interesting when you have interaction, because the differences depend on the level of the other factor. So we can actually sort of force it to do that, right? So we create the general linear hypothesis test, we put it in here, we calculate, or we display the summary of that, doing the Bonferroni adjustment. If we didn't do it, if we didn't specify this, it would automatically give the Tukey, because we specified that before, and we can get these differences. But these differences are not that interesting. Okay. All right. So I'm going to skip all that. All right. So what should we do in this case when we have interaction? Okay. If we jump down to section 5.3, I'll show you how to use the package lsmeans to look at conditional comparisons. And this is one of the few packages that I use in my own work regularly. That was written by Russell Linth. He got his PhD here at UNM about 40 years ago. And he's very well known for his online power calculators. He's done quite a bit with response surface methodology, and a really generous guy too. He's contributed to the graduate program monetarily here at UNM. So lsmeans allows us to compare cell means, which is what we want to do, but when we can't get it with the general linear hypothesis test. Basically, I'm going to tell you that lsmeans you can always use. It's always going to give you the right answer. Always use that. We will use general linear hypothesis testing later in the semester. I wanted to show you it a little bit this semester to get us acquainted. All right. So I guess I have one more comment there. When we have main effects models and the sample sizes are equal between groups, these two methods are going to agree, but lsmeans is always going to give us the right answer, whereas the general linear hypothesis test can sometimes be misleading. All right, so let's return to that battery example, and notice for this example, just temporarily, we're going to come back to the interaction model in a moment. First, we're going to look at the main effects model, which we know is not a good idea because there is interaction, but sit tight for a moment. So we're going to fit the main effects model. You can see that my linear model object over here has specifies that we've got max voltage, material type, temperature, but I didn't include the interaction, so I don't have that additional .mt as I've got in the interaction term that I created earlier. So if I do the general linear hypothesis test here, for example, comparing temperatures, it will give me this test, and I find that all are significant. All pairs are significant. The biggest one being obviously between 80 and 50 degrees of about 80 volts. And if we use the lsmeans package and use lsmeans, basically do the same thing, we have, let's see, can I get enough on the screen to convince you that it's the same result? Okay, so here's the general linear hypothesis test, and here is for lsmeans. There's a minus sign difference because of the order. The general linear hypothesis test is doing 65 minus 50, whereas lsmeans is going the other direction, 50 minus 65, but we have the same estimate, we have the same standard error. This tells us what the degrees of freedom is. We have a t-statistic and then the same p-value. So we're getting the same answer. In addition, lsmeans gives us the cell mean for that temperature, as well as a confidence interval. So it has a little bit more information. All right. It also tells us how the p-value was adjusted in the output and how the results are averaged over the materials. Okay. All right. When there are model interactions, we can get different results, and so that's where lsmeans is going to save us. So here is our interaction model again. Here I've just named it to have that interaction piece by my naming convention. Here we'll do the general linear hypothesis test, and we get this warning that we've got interactions, so beware. And here are the differences. So we've got basically 65 and 50 both give roughly the same estimate, with 85 and 65 difference being almost zero. Okay, let's see how lsmeans compares. So we're doing the same thing, and notice these differences are very different from what we saw with the general linear hypothesis test. So which ones should be believed? Let's see, I wanted to get both of those on the screen at the same time. Okay, these numbers up here are clearly different from these numbers. Okay. So both of them give you a warning. And my suggestion is to not interpret the main effects, generally speaking, when you have interaction. So this is where lsmeans allows us to interpret conditional factor level differences. So here is our interaction model again. No real need to To do it again, it's the same as it was before. And here is lsmeans, the interaction model, and this list, I've got a conditional. So what are the differences in material conditional on temperature? So let me scroll down a little bit. First thing we get are those means and confidence intervals, and you can see for temperature 50, here's the three materials, 1, 2, and 3, and these are the means for each of those, okay, as well as the confidence interval. And then it repeats with temperature 65 and temperature 80. Here are the pairwise differences. So we're doing the contrast between material types for temperature 50. And we're asking, is there a difference? And we're seeing for temperature 50, in terms of the corrected p-values, we're not really seeing much of a difference there for the material types. And we're going to scroll back up to the plot of the data to get a sense of whether we agree about this or not. For temperature 65, we're comparing material types, and here we find differences between material 1 and 2 and 1 and 3, but not 2 and 3. All right? And then for temperature 80, based on the p-values, no real differences. So the main result here is that for temperature 65, there was a difference between material type 1 versus the other two. All right, 65, material 1 versus the other two. That's our thing to remember. We can go the other way. We can do temperature conditional on materials. And we'll get, for material type 1, temperature 50, 134. These top numbers are going to be the same, just in a different order, right? So the number 134 is being the max voltage, is material type 1 at temperature 50. If I scroll up, material type 1, temperature 50, 134. Okay, so it's just ordering it differently. What is different is the pairwise comparisons. Here we're asking for material 1, which pairs of temperatures are different. So we have for material 1, 50 is different from the other two temperatures, but not the two highest temperatures. For material 2, that was the one that had a steady decrease. 50 and 65 are not quite different, but the extremes are very different, as well as the two high temperatures are different for material 2. And for material 3, we don't see a difference between the two low temperatures, but there's differences between both of the lower temperatures and the high temperature. Okay, and so those are really those are all the comparisons that we can make. So this is just saying lsmeans is the best, and if we scroll up to the image for this data, this is back on page 136. And if I can remember what, let's see, what did we have? We had for temperature 65, material 1 was different from the other two. That was the first conclusion we made. Temperature 65, another way to see that is temperature 65. That's the green one. The low, material 1 was different from the other two. So this green dot versus these two green triangles, they're all triangles. Then the other conclusion was for materials. For a given material, we had for material 1, the low temperature was different from the medium and the high temperature. For material 2, these two green temperatures weren't quite different, but the third was different from the first. And then for material 3, no difference, but the third temperature, 80, was different from the 50 and 65 temperatures. So the things that we saw on the plot came out in the statistical tests. Some things that we did see in the plot, for example, these two green points maybe seem different, but we don't have enough evidence to claim that they're different. So the main takeaways here is that we found an interaction in our model. We used lsmeans to give us the conditional comparisons when there was interaction. All right, so I'll come back and we'll check model assumptions, which will be very quick, and then we'll learn about how to deal with issues of non-constant variance, which we haven't needed to wrestle with yet.